Look up at the night sky and let yourself get lost in its vastness. Endless stars, galaxies swirling in the dark, mysteries stretching beyond comprehension. Now ask yourself this: what if everything you see, everything that exists, has happened before, not just once, but an infinite number of times? What if the universe itself is stuck in an endless loop of death and rebirth, a cosmic cycle where every ending is just the beginning of something new? This isn't science fiction. It's one of the most mind-bending ideas in cosmology, the theory that our universe might not be the first or the last, but part of an infinite sequence of cosmic resets. For thousands of years, humans have wondered whether time and existence move in cycles. Ancient Hindu texts spoke of universes breathing in and out, expanding and collapsing over incomprehensible spans of time. The Greeks imagined a cosmos that repeated itself in perfect, eternal symmetry. And today, some of the brightest minds in physics are uncovering evidence that these ancient visions might not just be myth, they could be a glimpse into the deepest truths of reality. From the ashes of one universe, another rises, carrying echoes of the past into a new dawn. So what does modern science really say about this staggering idea? Could the Big Bang have been just one moment in an infinite chain of cosmic rebirths? Are black holes, dark energy, or even the fabric of space-time itself holding clues to this grand cycle? Buckle up, because we're diving into the wild frontiers of physics, philosophy, and the very nature of existence. By the end of this journey, you won't just see the universe the same way again. You might start questioning what the end even means. The story of our universe as we know it begins with the Big Bang, an explosion of energy so immense that it set everything into motion. In a fraction of a second, space itself stretched outward, matter condensed, and the building blocks of galaxies, stars, and planets were forged. But what if that fiery birth was just half of the story? Picture the universe not as a one-time event, but as a cosmic heartbeat expanding, then contracting over and over again. This is the idea behind the Big Crunch, the hypothetical mirror image of the Big Bang, where all that exists reverses course, collapsing back into a single, infinitely dense point. For decades, scientists believed the fate of the universe depended on a single question: would gravity ever win? If there was enough matter pulling everything back together, the expansion would slow, stop, and reverse. Galaxies would rush toward one another, stars would collide, and space itself would shrink until the universe became a singularity once more. Some theories even suggest that the Big Crunch wouldn't be the end. Instead, it could trigger another Big Bang, resetting the cosmic clock and starting the cycle anew. But here's where things get really interesting. The Big Crunch isn't just a poetic idea, it's grounded in real physics. Einstein's equations hinted at the possibility, and early models of the universe assumed this cycle was inevitable. Then, in the 1990s, astronomers made a shocking discovery. The expansion of the universe wasn't slowing down, it was speeding up, driven by a mysterious force we now call dark energy. This threw the Big Crunch into question. If the universe keeps stretching faster, how could it ever collapse back? Yet some physicists refuse to let the idea die. They propose that dark energy might not be constant, that its influence could fade over time, allowing gravity to regain control billions of years from now. Others suggest that our universe is just one bubble in a vast multiverse, where some regions collapse while others expand forever. The debate is far from settled, but one thing is certain: whether the Big Crunch is real or not, the very possibility forces us to rethink our place in the cosmos. What if everything we see is just a single act in an endless cosmic play, where the stage resets after each performance? The answers may lie in black holes, quantum fluctuations, or even hidden dimensions, clues waiting to be uncovered in the fabric of reality itself. Long before telescopes peered into deep space or equations described cosmic expansion, ancient cultures were already wrestling with the nature of time itself. Take the Hindu concept of Kalpas, vast epochs spanning billions of years, where universes are born, flourish, and dissolve like bubbles in an endless ocean. Each Kalpa begins with the out-breath of the creator god Brahma, birthing galaxies and life, only to end in a cosmic inhale, collapsing everything back into stillness before the cycle renews. What's astonishing isn't just the poetic imagery, it's the eerie resemblance to modern theories of oscillating universes, where expansion and contraction repeat across aeons. Across the globe, the Maya carved their vision of cyclical time into stone. Their long-count calendar didn't just track days, it mapped cosmic cycles so precise they aligned with celestial events down to the minute. The end of each cycle, like the much-debated 2012 phenomenon, wasn't a doomsday prophecy but a reset button. The Maya saw time as a spiral where history's patterns recurred, layered with new meaning, a perspective that mirrors today's debates over whether the universe might repeat its own patterns in each rebirth. Then there were the Greeks who wove cyclicality into philosophy. Stoic thinkers like Chrysippus imagined a universe consumed by fire ekperosis only to be reborn identical to the last, replaying every moment, every life in infinite detail. Even Plato hinted at cosmic recurrence, suggesting perfect forms echoed through time. These weren't just myths, they were attempts to explain the same paradoxes physicists grapple with now, how something could emerge from nothing or whether time has a true beginning. What unites these ancient ideas isn't just their audacity, it's their insistence that destruction isn't an end but a transformation. When Hindu texts describe universes dissolving into the causal ocean, or Mayan glyphs depict gods remaking the world, they're echoing a truth modern science is only beginning to test, that the cosmos might not be linear but rhythmic. The real marvel, these cultures, separated by continents and millennia, arrived at versions of the same profound insight without a single equation. Einstein once believed the universe was eternal and unchanging, a perfect, static masterpiece frozen in time. In 1915, his general theory of relativity revolutionized our understanding of gravity, but it came with a cosmic headache. The equations insisted the universe should either be expanding or contracting, not standing still. This troubled him deeply. If the universe wasn't static, it implied a starting point, a beginning, and that idea clashed with the prevailing view of an eternal cosmos. So Einstein did something bold. He tweaked his own equations, adding a fudge factor he called the cosmological constant, a mysterious repulsive force that would counteract gravity's pull, keeping the universe balanced in perfect equilibrium. For a while, it seemed like a stroke of genius. The cosmological constant stabilized his model, preserving the timeless universe scientists of the era expected. But then came Edwin Hubble's groundbreaking observations in the 1920s. Peering through the Mount Wilson telescope, Hubble discovered something extraordinary. Distant galaxies weren't just floating in place, they were racing away from us. The universe wasn't static at all. It was expanding, stretching space itself like the surface of an inflating balloon. Einstein realized his mistake. The cosmological constant, once his saving grace, now seemed unnecessary. He famously called it his greatest blunder, abandoning the idea entirely. Yet history has a way of circling back. Decades later, the cosmological constant made an unexpected comeback. In the 1990s, astronomers found that the universe's expansion wasn't just continuing, it was accelerating, as if some invisible energy was pushing galaxies apart faster and faster. Suddenly, Einstein's blunder didn't look so foolish anymore. Scientists revived the cosmological constant, repurposing it as a way to explain dark energy, the enigmatic force driving this accelerated expansion. But here's the twist. If dark energy behaves unpredictably, weakening over time or even reversing, it could set the stage for a cosmic collapse. The very idea Einstein discarded might hold clues to a cyclical universe where expansion gives way to contraction and the cycle begins anew. This roller coaster of scientific thought reveals something profound. Even mistakes can light the path to deeper truths. Einstein's static universe may have been wrong, but his cosmological constant opened doors to questions we're still grappling with today. Could dark energy be the key to a universe that breathes in and out? Or is the cosmos destined to expand forever, cold and empty? The irony is rich. A concept born to preserve eternity might end up explaining how universes live, die, and are reborn. Einstein's legacy isn't just in the answers he found, it's in the questions he left behind, echoing across the ages. Imagine a universe that never truly dies. Instead, it bounces back like a cosmic rubber band, expanding to its limit before snapping back into a singularity, only to explode outward again in a never-ending cycle of rebirth. This mesmerizing idea, known as the oscillating universe theory, gripped physicists in the mid-20th century as a tantalizing alternative to a one-and-done Big Bang. At its core, the theory offered an elegant symmetry, no need for a definitive beginning or end, just an eternal rhythm of creation and destruction. The math seemed to support it. Einstein's equations allowed for scenarios where a universe filled with enough matter would eventually slow its expansion, halted by gravity's relentless pull. From there, the collapse would begin, galaxies merging, temperatures soaring, space itself crumpling until everything converged into a searing hot singularity. But instead of fading into oblivion, this ultra-dense state could trigger another Big Bang, birthing a fresh universe with its own galaxies, stars, and perhaps even life. A perfect cosmic reset, but cracks soon appeared in this elegant vision. The most glaring problem, entropy, the universe's tendency toward disorder. With each cycle, entropy would increase, meaning every subsequent universe would emerge more chaotic than the last. Over infinite cycles, this buildup would leave the cosmos a featureless, lifeless void, devoid of the structure needed for galaxies or planets. It's like photocopying a document repeatedly. Each version loses clarity until nothing legible remains. By the 1970s, this entropy problem cast serious doubt on the oscillating model. Yet science never stands still. Modern theorists have revived the concept with bold twists. Some suggest that during the Big Crunch, quantum effects could erase entropy, scrubbing the cosmic slate clean. Others propose that our universe is just one layer in a higher dimensional reality, where collisions between membranes, think of them as cosmic soap bubbles, spark new Big Bangs without a collapse phase. These ideas, while speculative, breathe new life into the cyclical universe debate. What's fascinating isn't just the science, it's the philosophical weight of these theories. An oscillating universe erases the anxiety of a definitive end, replacing it with a grand, eternal recurrence. Nietzsche once mused that in an infinite cosmos, every moment might replay identically forever. But modern physics paints a subtler picture, cycles with variations where each universe could rewrite its own rules. Whether the oscillating model holds or falls, it reminds us that the cosmos is far stranger and more resilient than we ever imagined. What if black holes aren't the end of information, but cosmic messengers carrying echoes of one universe into the next? Roger Penrose, the Nobel Prize-winning physicist who helped decode black holes, dared to ask this question, and his answer upended everything we thought we knew about cosmic cycles. His conformal cyclic cosmology theory paints a universe without beginning or end, where time itself resets in vast epochs called eons. Picture this: our universe expands until all matter fades into radiation, galaxies dissolve into light, and space becomes an empty sea of identical particles. At this point, Penrose argues, the universe loses any sense of scale. It's mathematically identical to the ultra-dense singularity of a new Big Bang. The end of one eon becomes the birth of the next, an endless chain of cosmic reincarnation. But here's the twist that makes Penrose's vision radical. Information isn't lost in the transition. black holes, those notorious cosmic shredders, might actually encode data from one cycle to another through Hawking radiation, the faint energy they emit as they evaporate. Penrose suggests that this radiation leaves imprints on the boundary between eons, like fingerprints on a cosmic window. These imprints, called Hawking points, could appear in the cosmic microwave background, the afterglow of our Big Bang, as mysterious hotspots, hints of a universe that came before ours. Critics argue that conformal cyclic cosmology stretches the limits of known physics, especially around how information could survive such extreme conditions. Yet Penrose's math holds a haunting elegance. If he's right, the night sky isn't just a snapshot of our universe, it's a palimpsest, layered with faint traces of eons long gone. Imagine standing on a beach where every grain of sand holds the history of a prior world waiting to be decoded. This isn't just about black holes or radiation, it's about rewriting the very meaning of time. The implications ripple outward. If universes repeat infinitely, could the same stars, planets, or even civilizations emerge again and again? Penrose avoids such sci-fi speculation, focusing instead on the math. But the theory forces us to confront a dizzying possibility, that our universe is both ancient and newborn, a single note in an infinite cosmic symphony where every ending is a prelude. Whether CCC withstands future tests or not, it challenges us to see the cosmos not as a one-time event, but as something far stranger, a story with no first page and no last. Black holes have long been seen as cosmic dead ends, monstrous pits of gravity where light, matter, and even time itself vanish forever. But what if we've had it all wrong? Imagine these gravitational giants not as tombs, but as cosmic wombs, birthing entirely new universes in their depths. This mind-bending idea comes from physicist Lee Smolin, who proposed a theory so radical it redefines the very fabric of reality: cosmic natural selection. Picture a black hole collapsing inward, its singularity stretching space-time to such extremes that it triggers a new Big Bang, not in our universe but in a separate, hidden dimension. Each black hole could be a seed, spawning a fresh cosmos with its own laws of physics, stars, and perhaps even black holes of its own. Smolin's theory flips the script on Darwinism, applying evolution to the universe itself. Just as life adapts to its environment, universes might evolve to maximize black hole production. Think about it, a universe with slightly tweaked physics, say, a stronger gravitational constant, could forge more black holes, which in turn birth more universes inheriting those traits. Over countless generations, universes fine-tune themselves to become black hole factories, explaining why our own cosmos seems perfectly calibrated for their creation. It's survival of the fittest on a scale so vast it defies comprehension, a fractal multiverse where every black hole is a doorway to infinity. Critics argue that Smolin's idea leans heavily into speculation, with no direct way to test whether daughter universes exist. But the implications are staggering. If true, black holes aren't just destructive, they're creative forces, weaving an endless tapestry of realities. Some universes might fizzle out, their physics too unstable for black holes to form. Others could flourish, spawning lineages of cosmic offspring. And here's the kicker: if these baby universes inherit traits from their parents, our own existence might hinge on a chain of cosmic ancestry stretching back to an unknowable original. The beauty of Smolin's vision lies in its audacity. It transforms black holes from grim reapers into architects, threading the needle between destruction and creation. Whether the theory holds or not, it forces us to confront a dizzying thought: that every galaxy-devouring singularity might be writing the first chapter of another universe's story, one where the cycle begins anew. In this grand view, death isn't an end, but a metamorphosis, echoing the ancient truth that endings are often beginnings in disguise. Picture our universe not as a solitary bubble floating in emptiness, but as a single sheet of reality drifting through higher dimensions, a brane, short for membrane. This is the wild premise of string theory, where the fabric of existence isn't just three-dimensional space, but a vast cosmic landscape of hidden dimensions vibrating with energy. Now imagine another brain parallel to ours, invisible yet just a whisper away in this higher dimensional void. What happens when these cosmic sheets collide? According to the ekpyrotic universe model, the answer is nothing short of spectacular, a collision so violent it could ignite a new Big Bang, resetting the cosmic clock without the need for a crushing singularity. String theory, often called the theory of everything, suggests that the fundamental particles we know, quarks, electrons, photons, aren't dots but tiny, vibrating strings. These strings oscillate in up to 11 dimensions, far beyond the 3 we experience daily. But here's where it gets mind-bending. Some versions of the theory propose that entire universes, including ours, could exist as three-dimensional brains floating in a higher dimensional space called the bulk. Think of it like slices of bread in an infinite loaf, where each slice is a separate universe with its own laws of physics. The ekpyrotic model takes this further. Instead of a Big Bang emerging from a single point, it posits that our universe began and could begin again, when two brains smacked into each other like cymbals in the dark. The energy of that collision would flood our brain with heat and matter, mimicking the fiery birth we call the Big Bang. But unlike the traditional model, this wouldn't be a one-time event. If brains oscillate through the bulk, drifting apart and crashing together in an endless dance, each collision could spawn a new cosmic cycle, a universe reborn from the wreckage of the last. Critics point out the glaring challenge. We can't observe these extra dimensions or the bulk directly, but supporters counter with subtle evidence. The cosmic microwave background, that faint glow from the early universe, bears patterns some argue could be echoes of brain collisions, ripples from a cosmic fender bender billions of years ago. Others suggest that gravity's unusual weakness compared to other forces might hint at its ability to leak into higher dimensions, a clue that we're living on a brain in a much larger reality. The implications are staggering. If the ekpyrotic model holds, the Big Bang wasn't a beginning, just a turning point in an eternal rhythm of collisions. Each cycle might tweak the laws of physics slightly, meaning universes could evolve, with some fostering life and others fading into barren voids. It's a vision both humbling and exhilarating, an infinite multiverse where endings are just preludes, and every cosmic dawn is written in the hidden geometry of dimensions we've yet to see. Dark energy is the universe's greatest unsolved riddle, an invisible force pushing galaxies apart at ever-increasing speeds, as if the cosmos itself is in a hurry to escape its own shadow. Discovered in the late 1990s when astronomers measured distant supernovae and found they were dimmer than expected, dark energy shattered the assumption that gravity would someday slow the universe's expansion. Instead, it revealed a reality far stranger. Space isn't just growing, it's accelerating. Picture blowing up a balloon with no intention of stopping, where every dot on its surface races away from the others faster and faster. That's our universe under dark energy's grip. But what if this acceleration isn't the final word? Some theories suggest dark energy might not be constant. It could weaken over time or even flip into an attractive force, pulling the universe back together. Imagine a rubber band stretched to its limit, then suddenly snapping back. If dark energy's repulsive push fades, gravity could regain control, reversing the expansion into a collapse. This scenario, known as the Big Crunch, would see galaxies hurtling toward one another, temperatures soaring, and space itself crumpling into a fiery singularity, a reset button for the cosmos. The key lies in dark energy's nature, which remains one of physics' greatest mysteries. Is it a property of empty space itself, as Einstein's cosmological constant suggests? Or is it a dynamic field, like an invisible fluid filling the universe, capable of changing its behavior over eons? The latter possibility opens the door to cyclical models. If dark energy decays, the universe's expansion could slow, halt, and reverse. But if it strengthens, the cosmos might rip apart atom by atom in a big rip, leaving no chance for rebirth. Here's where things get speculative yet tantalizing. Some cyclical theories propose that dark energy's influence could wax and wane in cycles, driving expansion and contraction like a cosmic pendulum. Others suggest that dark energy's effects might vary across different regions of space, creating pockets where new universes bubble into existence. The James Webb Space Telescope and next-generation observatories aim to measure dark energy's behavior with unprecedented precision, hunting for clues in the way galaxies cluster and light bends across the cosmos. What makes dark energy so fascinating isn't just its power to shape the universe's fate, it's the philosophical weight it carries. If dark energy fades and cyclicity prevails, our universe might be one chapter in an endless saga. If it dominates eternally, we could be drifting toward an irreversible dispersal, a quiet fade into darkness. Either way, dark energy forces us to confront a humbling truth. The cosmos plays by rules we're only beginning to decipher, and its ultimate destiny might hinge on an invisible force we still don't understand. Here's a paradox at the heart of cosmic rebirth. If the universe is trapped in an endless loop, why doesn't it get more chaotic with every cycle? This is the tyranny of entropy, the relentless march of disorder that makes scrambled eggs out of pristine kitchens and turns stars into cold, scattered dust. According to the second law of thermodynamics, entropy always increases over time. It's the universe's way of forgetting, erasing structure into a bland, uniform soup of particles. So if the cosmos collapses and rebounds again and again, why hasn't it already devolved into total chaos after countless cycles? The problem haunted early proponents of oscillating universes. Each big crunch would compress matter and radiation into a fiery singularity, but entropy would pile up like unpaid debts. Imagine blowing up a balloon, deflating it, then blowing it up again. But each time, tiny wrinkles accumulate until the surface becomes a crumpled mess. Eventually, the balloon can't hold its shape. By that logic, after enough cycles, the universe should be a formless void, unable to birth galaxies or life. Yet here we are in a cosmos brimming with structure, from swirling galaxies to the delicate double helix of DNA. This contradiction seemed to doom cyclic models until physics fought back with some of its wildest ideas. One escape hatch comes from Roger Penrose's conformal cyclic cosmology. He argues that when the universe expands far enough, all matter decays into massless particles like photons, leaving nothing but a sea of uniform radiation. At this point, the cosmos loses any sense of scale. A universe stretched to infinity looks mathematically identical to one crushed into a singularity. Penrose calls this conformal rescaling, a cosmic reset button where entropy gets erased, allowing the next cycle to begin fresh. It's like taking a faded, wrinkled painting and stretching it until every detail blurs into blank symmetry, then using that blankness as a fresh canvas. Critics question whether information truly vanishes or just becomes inaccessible, but if Penrose is right, the universe has a built-in eraser for its own chaos. Then there's the quantum twist. Some theorists suggest that at the moment of collapse, quantum gravity effects could dominate, scrambling entropy like shuffling a deck of cards. In ordinary physics, shuffling increases disorder, but quantum mechanics plays by different rules. At microscopic scales, particles can tunnel through barriers or exist in multiple states at once. Apply this to a collapsing universe, and quantum fluctuations might reprocess entropy, redistributing it randomly rather than letting it accumulate. Picture a cosmic laundromat where the stains of the previous cycle get washed out by the turbulence of quantum uncertainty. The stakes couldn't be higher. If entropy can't be reset, cyclic models collapse under their own weight. But if physics finds a way, whether through conformal rescaling, quantum reboots, or something even stranger, the universe might dance forever, its chaos tamed by the same laws that create it. This isn't just about cosmology, it's about time itself. The arrow of time, the reason we remember the past but not the future, is tied to entropy's rise. If cycles can restart, does time loop too? Or does each new universe carve its own irreversible path? The answers could rewrite not just our cosmic story, but our understanding of existence itself. What if the Big Bang wasn't the beginning of everything, but just a cosmic turning point, a moment when the remnants of a previous universe gave birth to ours? Quantum physics offers a dizzying possibility that our universe didn't emerge from nothingness, but from the seething, probabilistic chaos of a pre-existing quantum foam. Picture a roiling ocean where particles flicker in and out of existence, where space and time lose their familiar shapes, and reality itself becomes a blur of potential. In this quantum realm, the distinction between before and after melts away, hinting that the Big Bang might have been less of a creation event and more of a transformation. This idea stems from the bizarre behavior of quantum fluctuations, tiny, unpredictable shifts in energy that occur even in the emptiest reaches of space. In our everyday world, these fluctuations are barely noticeable, but under extreme conditions like those near a black hole or in the universe's earliest moments, they can warp spacetime itself. Some theories suggest that in the dying moments of a prior universe, these fluctuations could have grown so wild that they triggered a new expansion, like a wave cresting and crashing into a fresh cycle. The Big Bang, then, wouldn't be a singular origin, but a bridge between cosmic epochs. One of the boldest takes on this concept comes from loop quantum gravity, a framework that reimagines spacetime as a network of tiny, woven threads. In this view, the collapse of a previous universe wouldn't end in a singularity, a point of infinite density, but would instead rebound when quantum effects resist further compression, like a spring recoiling. The universe would bounce, transitioning from contraction to expansion without ever reaching utter destruction. Evidence for this big bounce might lie in subtle patterns imprinted on the cosmic microwave background, the faint afterglow of our universe's fiery youth. If these patterns match the predictions of quantum gravity models, we could be staring at echoes of a universe that came before ours, but the quantum story gets even stranger. Some hypotheses propose that universes can spontaneously arise from nothing more than fluctuations in a timeless, spaceless void. In this scenario, the before of the Big Bang isn't another universe, but a formless sea of potential where probabilities reign. A particularly large fluctuation could have nucleated our cosmos like a bubble forming in boiling water, with the laws of physics crystallizing as it expanded. This wouldn't require a predecessor universe at all, just the inherent instability of quantum nothingness. The challenge, of course, is testing these ideas. Quantum effects are notoriously elusive, especially when scaled to cosmic proportions. Yet experiments with particle accelerators and observations of the early universe's faint signals might one day reveal clues. Did our universe inherit quantum fingerprints from an earlier cycle, or did it emerge from pure potential, a cosmic accident with no past at all? Either way, quantum physics blurs the line between beginning and transition, suggesting that even the Big Bang might be just one step in an infinite dance of creation. If our universe is part of an infinite multiverse, then cosmic rebirth might not be a solitary event. It could be happening everywhere all at once in ways we can barely fathom. Picture a vast, bubbling cauldron of spacetime where new universes constantly sprout like foam on the surface of an ocean, each with its own unique physics, its own history, its own fate. This is the wild landscape of eternal inflation, a theory that reshapes the very idea of cyclical time into something far more expansive and far stranger. The concept hinges on the behavior of the inflatoned field, a mysterious energy that drove the universe's exponential expansion in the first fractions of a second after the Big Bang. In most models, inflation shuts off as suddenly as it began, leaving behind the orderly cosmos we know. But eternal inflation suggests something more radical, that in some regions of space, inflation never stops. Instead, it keeps stretching spacetime at a breakneck pace, while in other pockets the field relaxes, allowing new universes to pinch off like bubbles in a boiling pot. Each of these bubble universes becomes its own self-contained cosmos, potentially with different physical constants, dimensions, or even laws of nature. Now, here's where cyclic models collide with multiverse theory. Traditional cyclic universes, like Penrose's Conformal Cosmology or the Big Bounce, focus on a single universe dying and reborn in a closed loop. But in the multiverse, cycles aren't synchronized, they're chaotic, infinite, and decentralized. Some bubbles might collapse and rebound while others expand forever. Some could collide with neighboring universes, triggering new inflationary surges, while others drift alone in the void. Imagine a forest where some trees shed leaves in autumn only to regrow them in spring, while others wither entirely, making space for new saplings to rise. The multiverse isn't one story repeating, it's an endless library where every book has a different ending or no ending at all. Yet even in this sprawling cosmic landscape, traces of cyclicity linger. Some versions of string theory suggest that colliding branes, those higher dimensional membranes, could create not just one big bang but countless ones across the multiverse. Each collision resets a local region of spacetime, embedding cyclical rebirth within an eternally inflating backdrop. It's a hybrid vision where universes recycle themselves, but not in unison, like clocks ticking at different rhythms across a vast, unseeable expanse. The implications are staggering. If eternal inflation is real, our universe might just be one accidental bubble in an infinite froth, destined to expand into cold solitude while new universes ignite nearby. Or perhaps, in some distant corner of the multiverse, another version of us is watching their own night sky, wondering if their cosmos is reborn like ours, or if they're floating in a one-shot reality with no second act. The beauty of these ideas isn't just their scale, but their defiance of simple answers. They force us to ask, is the cosmos a solitary phoenix, rising from its ashes again and again? Or is it a boundless fire where every spark births something new? The truth might be stranger than either. Buried in the faint glow of the cosmic microwave background, the oldest light in the universe, might lie ghostly imprints of universes long gone. Roger Penrose's controversial claim centers on these patterns, dubbed Hawking points, strange circular hotspots in the CMB that radiate slightly more energy than their surroundings. According to Penrose, these aren't random fluctuations but cosmic tattoo scars left behind by black holes from a prior eon, their evaporation via Hawking radiation etching faint rings into the fabric of our newborn universe. It's a breathtaking idea that the death throes of ancient black holes could whisper to us across the abyss of a cosmic reset. The evidence hinges on meticulous analysis of CMB data from satellites like Planck. Penrose and his team argue that these points are too large, too uniform, and too anomalously warm to fit standard models of cosmic inflation, which predict a more randomized distribution of temperature variations. Instead, they align with predictions of how Hawking radiation, the elusive energy leaked by evaporating black holes, might manifest at the boundary between universes. Imagine tracing the outline of a shadow left by an object that no longer exists. Hawking points, if real, would be shadows cast by black holes that vanished before our universe began. But the scientific community remains sharply divided. Critics counter that the statistical significance of these points is shaky, that what Penrose identifies as anomalies could just be noise in the data, the cosmic equivalent of seeing faces in clouds. The Planck collaboration itself has pushed back, noting that rigorous analyses of the full dataset don't show the concentric patterns Penrose describes. Others argue that even if the points exist, They might stem from unknown physics within our universe, like exotic quantum fields or defects in space-time, rather than proof of a cyclical cosmos. The debate boils down to a fundamental question: are we seeing echoes of a deeper reality, or succumbing to the human tendency to find patterns where none exist? Supporters of Penrose's hypothesis aren't backing down. They point to independent studies that do find unusual correlations in the CMB, though none yet confirm Hawking points definitively. Some theorists suggest that future telescopes with even finer resolution might settle the debate by mapping the CMB's polarization, a kind of cosmic fingerprint that could reveal whether these hotspots carry the signature of evaporating black holes or something else entirely. What's at stake isn't just one theory's validity, but how far we're willing to let evidence stretch our imagination. If Hawking points are real, they'd be the first tangible clues that our universe is part of an infinite chain, each link forged in the fires of a previous collapse. If not, the search for cyclicity will have to pivot, but the allure of a universe that breathes in and out, again and again, will endure. After all, science thrives at the edge of the unknown, where today's controversy might become tomorrow's revelation. We think of time as an arrow always moving forward, never backward, with a clear past, present, and future. But what if that's just an illusion? What if time isn't a straight line at all, but a loop, a spiral, or even something stranger, a dimension where beginnings and endings blur into one? This is the radical possibility at the heart of cyclic cosmology, where the very nature of time might be rewritten with each cosmic rebirth. Take Julian Barber's controversial idea, timeless physics. In his view, time as we experience it doesn't exist at all. Instead, the universe is a vast collection of frozen moments, what he calls nows, stacked like frames in a film. Our perception of time flowing, of cause leading to effect, is just an emergent property, like watching individual still images flicker fast enough to create the illusion of motion. If Barber is right, then cyclic universes don't just reset matter and energy, they reset time itself. Each new cycle wouldn't be a continuation of the last, but a fresh arrangement of nows with no true before or after. This flips everything on its head. In a timeless cosmos, the Big Bang wouldn't be the start of time, just one configuration in an infinite gallery. Likewise, a big crunch wouldn't be an end, but a rearrangement like shuffling a deck of cards. Barber's model suggests that cycles aren't about time repeating, but about reality reconfiguring. It's a vision that echoes ancient philosophies like the Buddhist concept of samsara, the wheel of existence turning without beginning or end. Yet other cyclic theories do preserve time's arrow, just bending it into a circle. In these models, entropy still increases within each cycle, giving us the familiar flow from past to future. But when the universe resets, entropy resets too. Here, time is cyclical but not static. It's more like a spiral staircase. With each revolution, you return to the same point, but at a new level. This could explain why the universe isn't a featureless void after countless cycles, because each iteration isn't an exact copy, but a variation on a theme. The implications are dizzying. If time is truly cyclical, does that mean every moment is destined to recur? Does your life, with all its joys and sorrows, replay identically in every cycle, as Nietzsche's eternal return suggested? Or does each universe rewrite the script, allowing for infinite variations? The answer might lie in quantum mechanics, where probability reigns. If quantum fluctuations differ in each cycle, no two universes would ever be exactly alike, meaning time could be both cyclical and creative, a loop with room for novelty. The deeper we dig, the more time dissolves into paradox. Physics equations often work equally well whether time runs forward or backward, yet our lived experience insists on its one-way flow. Cyclic models force us to ask, is time's arrow a feature of the universe or just a quirk of our perception? Could a universe reborn remember its past, or would each cycle start with blank slate? These aren't just academic questions, they strike at the heart of what it means to exist in a cosmos without beginning or end. The more we question time, the more it slips through our fingers, leaving us to wonder whether we're chasing a fundamental truth or a phantom of the human mind. If the universe truly cycles through endless rebirths, what happens to our sense of meaning or even our free will, when every choice might repeat infinitely? Friedrich Nietzsche grappled with this very question in his Eternal Recurrence thought experiment. He proposed a chilling yet liberating test. Imagine a demon whispering that every joy, every pain, every mundane moment of your life will replay identically in an endless loop. Would you despair, or would you embrace it as the ultimate affirmation of existence? For Nietzsche, this wasn't just a metaphor, it was a litmus test for living authentically. Cyclic cosmology takes this idea from philosophy to physics, forcing us to confront whether our lives are fleeting sparks or echoes in an eternal chorus. Buddhist teachings offer a parallel vision with samsara, the wheel of rebirth where consciousness cycles through lives until enlightenment breaks the chain. But here's the twist: while samsara implies karma shaping each rebirth, cosmic cyclicity lacks such moral scaffolding. If universes reboot without memory, do our actions lose weight, or does the sheer scale of repetition render meaning not in linear progress, but in the beauty of each iteration? The contrast is stark. Samsara urges transcendence, while an endless quantum bounce might offer no escape, just variation. This tension spills into free will. If each cycle replays precisely, every decision is predetermined by the prior universe's collapse, a cosmic déjà vu stripping us of agency. But if quantum fluctuations introduce randomness, could each reboot allow for new choices, new histories? Some physicists argue that even in deterministic systems, chaos theory's butterfly effect ensures no two cycles are identical. Like a gardener pruning a bonsai tree differently each season, the universe might revisit themes without rigid repetition. Then there's mortality's sting. Human lives feel urgent because we assume a finite timeline, but what if death is just a comma in an infinite sentence? Cyclic models reframe extinction as transformation, where stardust isn't lost but recycled. The atoms in your hands might have forged stars in a past universe. Your thoughts could ripple in some future form. This isn't reincarnation, it's something grander, a dissolution into the cosmic loom where threads are rewoven without memory. Yet the haunting question remains: does infinity trivialize existence or amplify it? A one-shot universe lends weight to every moment, but endless cycles could render life a fractal pattern, unique yet recurring. Perhaps the answer lies in between, where cyclicity doesn't negate meaning but redefines it, not as a linear march but as a dance where every step, even if repeated, matters precisely because it's part of the music. Whether the cosmos forgets or remembers, the awe of being here now, alive in this particular cycle, might be the only meaning we need. What if our universe isn't just cycling through rebirths but running on cosmic hardware? Simulation theory, the mind-bending idea that reality might be an artificial construct, collides with cyclic cosmology in ways that reshape both ideas. Picture this: instead of a universe collapsing and expanding through physical laws, it could be a vast computational process that periodically resets, like a video game loading a new level. The parallels are uncanny. Both theories dissolve the boundaries of what we consider real, suggesting that existence might be far more malleable and far stranger than we ever imagined. Consider how simulation arguments work. If an advanced civilization could create indistinguishable virtual worlds, the odds that we're living in base reality shrink. Now layer cyclic rebirth onto that. If the universe is a simulation, its big crunch might not be a gravitational collapse, it could be a system reboot. Suddenly, dark energy's acceleration looks less like a force of nature and more like a programmed countdown to the next iteration. Even quantum fluctuations, those ghostly blips of randomness, take on new meaning, Are they glitches in the code or deliberate seeds for variability between cycles? The overlap gets wilder when you examine fine-tuning. Our universe's constant gravity strength, the speed of light, are perfectly calibrated for life, as if dialed in by some unseen hand. Cyclic models explain this through endless trial and error, with each reset tweaking the rules slightly. Simulation theory offers a chilling alternative. Those constants aren't accidents or evolutionary byproducts, they're settings. Whether the universe is a self-correcting loop or a designed simulation, both roads lead to the same unsettling question. Are we just players in a game where the rules were written long before us? Yet contradictions emerge. Simulation theory often assumes an external programmer, some higher intelligence running the cosmic server. Cyclic cosmology, by contrast, needs no outside influence. The universe is its own engine of renewal. But what if these aren't competing ideas, but two faces of the same truth? Imagine a universe that's both cyclic and simulated, where each bounce is an upgrade installed by its own future civilizations. The descendants of humanity or some alien intelligence could become the gods of their own past, tweaking the parameters of each new cycle to avoid heat death or entropy's grip. It's a closed loop of creation where the simulated become the simulators, and reality is a snake eating its own tail. The real test lies in evidence or the lack of it. Simulation theorists hunt for pixelation in spacetime or anomalies in quantum behavior, while cyclic cosmologists scour the cosmic microwave background for Hawking points. Both searchers grapple with the same problem. How do you prove you're inside the system when all your tools are part of it? Maybe the answer isn't in finding cracks, but embracing the paradox. Whether we're living in a cosmic rerun or a machine's dream, these theories force us to confront the fragility of reality itself, and the humbling possibility that beginnings and endings might just be someone else's save points. For all their poetic grandeur, cyclic universe models face a harsh reality check. Science demands evidence, and many of these ideas stretch the limits of what we can observe or test. Take Roger Penrose's conformal cyclic cosmology. While its elegance captivates theorists, critics point out that without definitive proof of Hawking points in the cosmic microwave background, the theory remains a beautiful speculation. The Planck satellites' detailed maps of the CMB haven't yet confirmed the concentric rings Penrose predicted, leaving his model in a precarious limbo between genius and guesswork. And even if such patterns exist, could they truly distinguish CCC from other anomalies, like gravitational waves or quantum field fluctuations? The line between groundbreaking discovery and cosmic pareidolia, seeing shapes where none exist, is perilously thin. Then there's entropy, the relentless foe of all cyclical theories. The second law of thermodynamics insists that disorder must increase over time, yet cyclic models require a near-miraculous entropy reset with each rebirth. Penrose's conformal rescaling offers a mathematical workaround, but skeptics argue it's more sleight of hand than solution. If entropy isn't truly erased, just hidden through geometric trickery, wouldn't the universe still accumulate chaos over infinite cycles, eventually devolving into a featureless void? Defenders counter that quantum gravity effects near a big crunch might rewrite the rules entirely, but without a unified theory of quantum gravity, this remains a hopeful assumption, not a proven mechanism. The Big Bounce hypothesis faces its own hurdles. While loop quantum gravity provides a tantalizing framework for a singularity-free rebound, no observational data yet confirms that our universe emerged from a prior collapse. The telltale signatures, specific patterns in the CMB's polarization, or deviations from standard inflation's predictions remain elusive. Worse, some calculations suggest that even a quantum bounce couldn't fully reset entropy, meaning each cycle might still grow progressively messier until structure becomes impossible. It's like trying to rebuild a sandcastle after the tide washes in. Each attempt leaves the grains more scattered than before. Competing theories further muddy the waters. Eternal inflation, for instance, renders cyclicity moot by proposing an endlessly sprouting multiverse where individual bubbles live and die without overarching rhythm. String theory's landscape of possible universes suggests that physical constants might vary randomly across space-time, not recycle predictably. Even dark energy's stubborn persistence challenges cyclic models. If expansion accelerates forever, collapse becomes impossible, leaving no path for rebirth. Yet the debate's very existence underscores science's vitality. Cyclic cosmologies push us to ask deeper questions. What does proof mean when studying phenomena beyond our cosmic horizon? How do we test theories that span eons? Whether these models ultimately succeed or fail, their value lies in stretching our imagination, forcing us to confront the profound, unsettling idea that our universe might be both ancient and ephemeral, one note in an infinite symphony we're only beginning to hear. The idea of a big crunch collapsing into a singularity has always carried a sense of finality, a point where physics as we know it breaks down and the universe hits a hard reset. But what if there's no singularity at all? Enter loop quantum gravity, a radical framework that reimagines space-time not as a smooth continuum, but as a woven tapestry of tiny, indivisible threads. In this view, the universe doesn't collapse into an infinitely dense point. It reaches a threshold where quantum effects kick in like a cosmic safety net, bouncing back before singularity can form. This is the Big Bounce, a universe so resilient it rebounds like a ball hitting the floor, turning collapse into rebirth without ever touching true annihilation. Picture the final moments of a contracting universe. Galaxies merge, temperatures soar, and space itself contracts to scales so small that quantum gravity dominates. Here, the fabric of reality isn't smooth, it's granular, like pixels on a screen. Loop quantum gravity predicts that this granularity creates a repulsive force, a kind of quantum pressure that grows stronger as space compresses. Instead of crumbling into oblivion, the universe hits this pressure wall and springs back outward, triggering a new Big Bang. No infinite densities, no lawless singularity, just a seamless transition from contraction to expansion, like a pendulum swinging back after reaching its lowest point. Now contrast this with Roger Penrose's conformal cyclic cosmology. In CCC, the universe doesn't bounce, it resets. Matter decays into radiation, entropy vanishes through conformal rescaling, and the end state becomes mathematically identical to a new Big Bang. It's less like a rebound and more like a cosmic reincarnation where the universe forgets its past entirely. The Big Bounce, by contrast, suggests continuity. Quantum effects preserve some structure, meaning information, though scrambled might carry over. It's the difference between a book ending and restarting from page 1 versus a story where the final chapter bleeds into a new prologue with whispers of the old narrative lingering. Evidence for either model remains elusive, but subtle clues might lurk in the cosmic microwave background. CCC predicts Hawking points anomalous hotspots from ancient black holes, while the Big Bounce could leave distinct imprints in the CMB's polarization patterns, like echoes of pre-bounce gravitational waves. The real challenge is that both theories push beyond the limits of current observation. Without a unified theory of quantum gravity, we're left with mathematical elegance versus empirical silence, a tantalizing standoff between imagination and proof. The philosophical stakes are just as gripping. If the Big Bounce is real, our universe might carry spectral remnants of its predecessors, like scars from a past life. If CCC holds, each cycle is a blank slate with no memory of what came before. One offers cyclical continuity, the other cyclical amnesia. Both force us to ask, is the cosmos a story with endless sequels, or a single tale told over and over, each time as if for the first time? One of the most promising ways to test cyclic universe theories lies in the faint ripples of spacetime itself, primordial gravitational waves. These ripples, generated in the universe's earliest moments, would carry imprints of the violent processes that shaped cosmic history. If the Big Bang was preceded by a big crunch, those waves might bear distinct signatures, subtle deviations from the patterns predicted by standard inflation. Future observatories like the Laser Interferometer Space Antenna, or LISA, could detect these whispers from the dawn of time. Unlike the fleeting gravitational waves from black hole mergers we observe today, primordial waves would stretch across the entire cosmos, a fossilized echo of collapse and rebirth. Their frequency, amplitude, and polarization could reveal whether spacetime endured a bounce or reset, offering the first direct evidence of a cycle. But gravitational waves aren't the only clue. The cosmic microwave background, that ancient light from 380,000 years after the Big Bang, is a treasure trove of hidden patterns. Cyclic models like Conformal cyclic cosmology predict concentric rings of temperature variation, Hawking points where black holes from a prior universe left their mark. The next generation of CMB telescopes, like the Simons Observatory or CMB-S4, aim to map this radiation with unprecedented precision. If these anomalies appear where Penrose's math predicts, it would be akin to finding fingerprints on the cosmic cradle, proving our universe wasn't the first. Then there's the enigma of dark matter. Some cyclic theories suggest it might not be an undiscovered particle but remnants of a previous cycle, black holes or exotic structures that survived the transition. Projects like the Vera Rubin Observatory, scanning the sky for gravitational lensing effects, could stumble upon strange distributions of mass that fit this idea. Even more speculative is the hunt for cosmic neutrinos, ghostly particles so elusive they might have slipped through a big crunch unscathed. Detecting a background neutrino signal with telltale energies could hint at a pre-Big Bang phase. Each of these experiments shares a common thread. They probe the edges of observability where the universe's deepest secrets hide. The challenge isn't just technical, it's philosophical. How do we test theories about events that might erase their own evidence? If the universe truly resets, what traces could possibly remain? The answers may lie in the subtle cracks between cycles, the imperfections in the cosmic reboot where the past bleeds through. Until then, we're detectives piecing together a puzzle where the pieces keep disappearing, and the stakes couldn't be higher. Confirming cyclicity wouldn't just rewrite cosmology, it would redefine our place in the grand scheme of existence. Imagine a civilization so advanced that death isn't just postponed, it's rendered irrelevant, not just across lifetimes but across cosmic cycles. If the universe truly reboots in endless loops, could intelligence find a way to persist through the chaos of collapse and rebirth? Science fiction has toyed with this idea for decades, from uploaded consciousness to digital afterlives. But strip away the fantasy and you're left with a staggering physics question. Could information, the essence of a civilization, survive the unimaginable violence of a big crunch or the searing reset of a conformal boundary? One audacious possibility lies in the most destructive objects in existence, black holes. These gravitational monsters are often seen as cosmic shredders, but their event horizons might also be the ultimate vaults. Theoretical physicists like Leonard Susskind have argued that black holes don't destroy information, they encode it on their surfaces like holograms, a concept known as the holographic principle. If true, a sufficiently advanced civilization might engineer black holes as libraries, imprinting their knowledge onto the horizon's quantum fabric. During a big crunch, those black holes would evaporate via Hawking radiation, potentially scattering their encoded data into the next cycle. It's like carving your story into a stone and tossing it into a volcano, trusting the ash to carry your words into the next epoch. But black holes aren't the only option. Quantum replication offers an even wilder path. In a phenomenon called quantum teleportation, particles can be disassembled in one location and perfectly reconstructed in another using entangled pairs, a process that preserves their quantum states. Scale this up, and you could imagine a civilization converting itself into quantum data, a pattern of information suspended in a field or crystal, waiting for the next universe's energy to reactivate it. The catch: quantum decoherence, the tendency for entangled states to collapse under interference, might erase the data long before the cycle resets, unless, of course, the civilization finds a way to shield its quantum archive from entropy, perhaps by anchoring it to topological defects in spacetime itself. Then there's the wild card of Boltzmann branes, a bizarre thought experiment where random fluctuations in a vacuum spawn self-aware entities. If the universe cycles infinitely, could consciousness emerge spontaneously in the chaos of each new bang, carrying forward some shadow of its predecessor? It's a haunting notion, intelligence not as a continuous thread, but as a recurring accident, flickering in and out of existence like a flame in the wind. The deeper you dig, the more these ideas blur the line between physics and metaphysics. If information persists, does identity? Would a civilization reborn from black hole data or quantum echoes truly be the same, or just a facsimile? And what happens to free will if the universe is locked in an endless replay, each iteration subtly altered by the remnants of the last? These aren't just thought experiments, they're stress tests for the very nature of reality. Whether through black holes, quantum tricks, or sheer cosmic luck, the dream of immortality might not be bound to a single universe, but woven into the fabric of time itself. The universe forgets, but the data perhaps remembers. If the universe truly repeats itself in perfect, infinite loops, then every choice you've ever made, every act of kindness, every moment of cruelty, would replay exactly the same way forever. This isn't just a cosmic curiosity, it's an existential gut punch. Nietzsche's eternal return wasn't just a thought experiment, it was a moral litmus test. If you knew your life would recur identically in endless cycles, would you despair at the futility, or would you live with such fierce intention that even eternity couldn't cheapen your actions? The ethical weight of this idea is staggering. If consequences don't accumulate across cycles, is there any real meaning to justice, growth, or redemption? Take something as simple as a lie. In a linear universe, deception might unravel over time, causing ripple effects that eventually return to the liar. But in a cyclical cosmos, the lie happens, resets, and happens again. No karmic fallout, no lesson learned. It's a closed loop of cause and effect with no net consequence. This challenges the very foundation of ethics, which assumes that actions matter precisely because they alter the future. If the future is predetermined to mirror the past, morality risks becoming a hollow performance, a script we're doomed to reenact without agency. Yet there's another way to see it. Perfect recurrence doesn't negate meaning, it amplifies it. Imagine every moment of joy you've experienced being repeated infinitely. The laughter of a child, the warmth of sunlight on your skin, the thrill of discovery, these aren't diminished by repetition. They're engraved into the fabric of existence. Conversely, suffering also recurs, which forces a brutal honesty. If a tyrant's cruelty or a systemic injustice repeats eternally, the urgency to confront it doesn't vanish, it becomes cosmic. Ethical imperatives might not hinge on changing an unchangeable future, but on aligning with values so vital they're worth reliving forever. The paradox deepens when you consider free will. If the universe is deterministic, replaying identical cycles like a cosmic record, then every thought you're having right now was predetermined billions of years ago. Your sense of choice is an illusion, and moral responsibility dissolves into physics. But quantum mechanics introduces randomness, tiny fluctuations that could make each cycle slightly different. Suddenly, there's wiggle room. Maybe your decisions don't rewrite the entire script, but they introduce variations like jazz improvisations on a timeless melody. Even in a cyclical cosmos, ethics could thrive in the spaces between certainty and chaos. And what of justice? Human systems rely on progress, wrongs addressed, imbalances corrected. But if time is a wheel, justice can't be deferred to some future reckoning. It must be realized now in each iteration. This reframes moral urgency. A cyclical universe doesn't excuse inaction. It demands that we live as if this iteration is the only one we'll ever get, because in a way it is. The Stoics understood this. Their concept of amor fati, love of fate, wasn't passive resignation but active embrace. If every moment returns eternally, then every moment must be worthy of eternity. The most unsettling question isn't whether actions matter, but what it means to matter at all. If the universe forgets nothing and forgives nothing, then our ethical struggles aren't just personal, they're etched into the cosmos. To live well isn't about altering an unchangeable cycle, but about finding a harmony so profound that even infinity can't erode its worth. The weight of forever doesn't crush meaning, it distills it to its purest form. From the silver screen to ancient legends, humanity has always been obsessed with the idea of cycles of lives relived, worlds reborn, and time folding back on itself. Take Christopher Nolan's Interstellar, where love and gravity transcend dimensions, bending time into a loop that allows a father to whisper across epochs to his daughter. The film's fifth-dimensional bookshelf isn't just a sci-fi spectacle, it's a metaphor for cyclic time, where past and future coexist, and every moment is eternally present. Then there's the first 15 lives of Harry August, Claire North's novel about a man who relives his life over and over, retaining memories of each cycle. His existence becomes a haunting dance of déjà vu and destiny, where every choice ripples through iterations, asking whether we're prisoners of repetition or architects of change. These stories resonate because they tap into something primal. The same awe that inspired myths like the Ouroboros, the serpent eating its tail, a symbol of eternal return found in Egyptian, Norse, and Aztec lore. The phoenix rising from its own ashes isn't just a bird. It's a promise that destruction isn't an end, but a prelude to renewal. Even modern franchises like Dark, Netflix's mind-bending German series, weave time into a knot where cause and effect blur, and characters become both creators and victims of their own loops. But why does this theme grip us so tightly? Perhaps because cycles soften the terror of endings. In a universe where everything fades, the idea that nothing is truly lost, that history rhymes if not repeats, offers a strange comfort. Or maybe it's the opposite, the horror of being trapped in a story you can't escape, like Bill Murray's weatherman in Groundhog Day, forced to relive the same day until he learns to be better. These narratives aren't just entertainment, they're thought experiments, testing what it means to be human in a cosmos that might not play by linear rules. The most fascinating part, these fictional cycles often mirror real scientific debates. Interstellar's time loops echo Penrose's conformal cosmology. Harry August's lives resemble quantum multiverse theories. When we watch these stories, we're not just escaping reality, we're rehearsing it, grappling with the same questions physicists ask. Whether through myth or movie, humanity keeps circling back to one idea, that the universe might not be a straight line, but a circle, a spiral, or something stranger still, a story we're telling ourselves over and over until we get it right. Is a cyclical universe the ultimate promise of renewal, or the cruelest form of eternal imprisonment? The answer depends on where you stand. For physicists like Roger Penrose, cyclicity offers a breathtaking symmetry, a cosmos that never truly dies but reinvents itself in endless variations. To philosophers like Nietzsche, it's a moral crucible, forcing us to confront whether our choices would still hold weight if repeated infinitely. But strip away the abstractions and you're left with a visceral question. Would living in a loop feel like paradise or purgatory? Consider the optimist's view. Cyclicity means no true end, no heat death, no irreversible fade into darkness. civilizations might rise and fall, but the universe itself persists, offering infinite chances for life, beauty, and discovery. It's the cosmic equivalent of a phoenix forever rising from its ashes. Some theorists even suggest that with each cycle, the laws of physics might tweak slightly, allowing for new forms of matter, energy, or consciousness we can't yet imagine. In this light, cyclicity isn't monotonous, it's evolutionary, a canvas so vast that every iteration could paint something unprecedented. Yet the pessimist's counter is brutal. If entropy isn't fully reset, each cycle could degrade further, leaving future universes more barren than the last. Even if information persists, what good is immortality if it's just an echo chamber? Jorge Luis Borges captured this horror in his short story, The Circular Ruins, where a man dreams another human into existence only to realize he himself is someone else's dream. A cyclical cosmos might trap us in someone else's recurring fantasy, stripped of free will, doomed to reenact the same drama with no exit. Philosophers like Arthur Schopenhauer saw cyclicity as tragic, a wheel of suffering with no off-ramp. Eastern traditions like Buddhism, however, offer a nuanced middle path. Samsara, the cycle of rebirth, isn't inherently good or bad. It's a school. The goal isn't to escape existence, but to awaken within it, refining one's karma until enlightenment breaks the loop. Apply this to cosmology, and cyclicity becomes less about repetition than refinement. Maybe universes like souls aren't stuck, they're learning, the most unsettling possibility. Both visions could be true. If each cycle introduces quantum randomness, some universes might spiral toward chaos while others evolve toward complexity. We could be living in one fortunate iteration where the dice rolled just right for galaxies, planets, and life, while countless others failed. It's a cosmic lottery where winning doesn't guarantee the prize lasts forever. But that's the irony. Whether utopia or dystopia, the cyclical universe forces us to reckon with impermanence. Even infinity, it seems, wears different faces. The real prison might not be the cycle itself, but refusing to see beyond the turn of the wheel. Picture the far future of our universe, not in billions but trillions of years. Stars have burned out, galaxies have drifted apart, and the cosmos has become a vast, dark graveyard where not even black holes remain. This is the heat-death scenario, the grim finale predicted by thermodynamics, a universe so stretched and diluted that temperatures approach absolute zero, all usable energy exhausted, and every process grinds to a halt. It's the ultimate fade to black, a silent, irreversible end where time itself loses meaning. But what if this isn't the finale? What if even in the coldest, emptiest void, the seeds of a new cycle lie hidden? The heat death seems inevitable if dark energy keeps accelerating expansion. Yet quantum physics whispers a counterargument: the vacuum of space isn't truly empty. It crackles with virtual particles popping in and out of existence, a quantum foam where the unimaginably rare can become inevitable given enough time. Enter quantum tunneling, the phenomenon where particles spontaneously teleport through barriers they shouldn't be able to cross. In a universe frozen near absolute zero, quantum fluctuations could, over eons, trigger a localized bubble of false vacuum decay. This bubble would rewrite the laws of physics within it, spawning a new Big Bang in an otherwise dead cosmos. It's like a single ember igniting in an endless tundra, a spark of rebirth where everything seemed lost. Vacuum decay offers an even wilder twist. Our universe might exist in a metastable state, a valley in the energy landscape of reality, stable but not perfectly so. A random quantum event could knock this valley into a lower energy state, unleashing a wave of destruction. But destruction isn't the end. As this wave propagates at light speed, it wouldn't just erase the old universe, it would create a new one in its wake with different fundamental constants and laws. The process would be catastrophic for anything in its path, but the resulting universe could be fertile ground for new cycles of complexity. It's cosmic demolition and reconstruction rolled into one. Critics argue these are statistical miracles requiring timescales so vast they might as well be infinite. Yet in an eternally expanding universe, even the improbable becomes certain. The real question isn't whether quantum rebirth is possible, it's whether anything meaningful persists across the divide. Would a new universe born from vacuum decay carry echoes of the old, or is it a total reset? And if consciousness somehow outlasts the transition, would it even recognize itself in a reality with alien physics? The heat death paints existence as a one-act tragedy. Cyclic rebirth, whether through quantum tunneling or vacuum decay, transforms it into an epic with no final curtain. One vision chills with finality, the other thrills with possibility. Both force us to confront a humbling truth that the cosmos operates on scales and mechanisms far beyond human lifespans, yet somehow we're here to ponder them at all. Whether the universe ends with a whimper or a reboot, the wonder isn't just in the answer, it's in the fact that we get to ask the question. From the ancient Hindus gazing at the stars and envisioning cosmic breaths to Roger Penrose studying the ghostly imprints of long-dead black holes, humanity's quest to understand the universe's cycles has always been a dance between myth and math. We've traced the echoes of these ideas through time across temple carvings, philosophical treatises, and equations scribbled on chalkboards, only to arrive at a truth as humbling as it is thrilling. The cosmos might not have a beginning or an end, just an endless rhythm of destruction and creation. The same mystery that haunted the Maya's calendars and Einstein's notebooks still haunts us today, dressed in new language but no less awe-inspiring. But here's the twist that lingers long after the equations fade. If the universe does reboot, would we ever recognize the signs? Imagine a civilization in the next cycle, scanning their night sky just as we do, finding the same cosmic microwave background, the same galactic patterns, the same puzzles. Would they mistake the echoes of our universe for the quirks of their own? Or would they, like Penrose, catch glimpses of something deeper, fingerprints on the edge of reality, hinting that they too are part of a story much older than their own Big Bang? The cruel irony is that even if cyclicity is real, the universe might erase its own evidence, leaving each new version to start from scratch, forever wondering if they're the first. So here's the question we're left with, hanging like a star in the void. Does it matter if we never know? Maybe the beauty isn't in solving the riddle, but in the act of asking, in the sheer audacity of a species huddled on a tiny rock, daring to decode the heartbeat of existence itself. After all, whether the cosmos loops or runs straight, we're here now, alive at the exact moment when the questions are as vivid as the answers are elusive. And isn't that the most cosmic joke of all? If this journey through time, space, and possibility left you staring at the night sky a little differently, hit that subscribe button, because the universe is full of mysteries and we're just getting started. Drop a comment below. If you could send one message to the next cosmic cycle, what would it say? The universe might forget, but let's make sure we don't.